All right, moving into section 8.3, confidence intervals for means, and this new thing called t-distributions. If you remember, everything that we've done so far in 8.2 had to do with proportions, going out, taking a sample, finding the percent of people that think something, and from that one sample saying, I know I got 32%, but I think the real proportion is somewhere between 30 and 34% or something, making it about proportions. Okay, now it's going to be the same game except for means. I'm going to go out and say, hey, what was your ACT score? And I'm going to come back with an average of 29.4, and from that I'm going to say, oh, I'm pretty sure that the average ACT score is somewhere between 26.4 and 32.4 or whatever I just said. I don't even know. So confidence intervals for means instead of proportions. In order to do that, we're going to have to work with this new thing called a t-distribution. Keep breathing. It'll be just fine. So to start with, here's something that will never, ever happen. This is kind of like a unicorn. If we were trying to find a confidence interval for a mean, and what you would think is you'd say, oh, it's x bar instead of p hat, plus or minus z star, and then we're going to use the standard error for means instead of the standard error for proportions. Duh, that formula is sigma over the square root of n. Here's the problem. How in the world could you possibly know sigma? Because to know sigma, you'd have had to know mu. And if you know mu, if you know the real mean from the whole population, why in the world are you going out and finding an x bar? That's nonsense, right? So here's the thing in this section. In the book, they start out by saying, hey, this could happen. Maybe sometime you'll be told what the standard deviation from the population was, and then you can go ahead and do this. The reality is that will never, ever, ever happen. That's a unicorn. You're not going to come across one. And so we're going to end up down here instead. There's no way that we could know sigma without knowing mu, because that's calculated using the mean, so it's impossible. But instead, we find the standard deviation from our sample. Not sigma, but s. Which means, okay, now we can't have sigma over the square root of n if we don't know n. We know s over the square root of n, right? Same game, except it's where did this standard deviation come from? It does not come from the whole population. It came from the sample. If it came from the sample, we're doing this. It's going to have a new name. It's not called the standard deviation anymore. It's going to be called the standard error. Fill it in here for me, Mr. G. It's called the standard error when we calculate it using s instead of sigma. This is where we're going to live in this section, because you would never ever know sigma. So this is where it gets a little interesting. Don't freak out. There seems like a lot of nonsense here. Instead of a normal distribution, as soon as we replace sigma with s, we don't have a uppercase N normal distribution anymore. We have something called a t-distribution. A t-distribution, if you just saw a picture with no labels, you'd think it was a normal distribution. It looks exactly the same, but it's just a little bit different. A standard normal curve is the same for any sample size. A t-distribution depends on the sample size. This part has never made any sense to me. We specify it by this thing called degrees of freedom. Degrees of freedom is always, always, always one less than the sample size. You got a sample of 50, guess what? Degrees of freedom, 49. You took a sample of size 10, degrees of freedom, 9. It's always that. And so we get this thing instead. We get, instead of x bar, that sample you got from your sample, plus or minus z star, the critical value for 95%, 99%, 90%, whatever, over this formula, which is impossible, we have this. Still x bar, because remember you went out and took one sample and you found an average. Plus or minus, now it's not z from a standard normal curve, it's t from a t-distribution. This, of course, the cool way to pronounce it is z star. The cool way to pronounce this, it's more southern, t star. It's really cool to say that. So be sure to walk around your house and tell your family t star, right? And then standard error, s the standard deviation that came from the sample, divided by the square root of the sample size. Degrees of freedom, always, 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 one less than your sample size. df, sample size minus 1, always. You're going to have to deal with that when you enter some things in your calculator in a little bit. So, a t-distribution, if you didn't know any better, if you saw a picture of a t-distribution, you would think it's a normal curve. This picture is the same as the picture that's in your book, and I'll show you that one in just a minute. It has a standard normal curve. That's the one that's solid, right? It's the tallest, and it has skinny little tails. The next one, the next tallest one, is a t with 9 degrees of freedom. That's pretty tall, almost like a normal curve. And it has tails that are a little bit fatter. It's almost like someone has taken it and they've smunched it down. If you smudge the top, the tails have to puff up a little bit. The dotted line here is a t-distribution with 2 degrees of freedom. That came from a really small sample size. So guess what happens? It's like someone has taken that standard normal curve and they have really smunched it down. And if you smunch it down, all that data's got to go somewhere. It puffs out of the tails, right? The higher the degrees of freedom, the closer it is to a standard normal curve. The lower the degrees of freedom, in other words, the smaller the sample size, the more smunched it gets and the fatter tails. Now, we're going to need to use that just like you could have used table A, but we used inverse norm to go find the critical Z star. Well, we're going to use our calculator, for the most part, to go find the critical T star, right? Now, there is a table B in the back of the book, and Mr. G spends a lot of time going through how you could use that. It is in your book. For our purposes, we are not going to. We're going to use this thing called inverse T on your calculator. Inverse T is the program. TI-84s, all the different TI-84s have inverse T on them, and I'll show you that in a minute. If you have a TI-83, you will need to, you will have to get a program and type it into your calculator. Or, frankly, ignore finding critical T stars for our purposes. But there is a link on the Chapter 8 document where you can get that. You would have to enter a few lines of code. It's not very hard, but it's not on the TI-83s. It's a pretty easy program. All the code will be linked, and I'll show you that, but you would have to type it in. So that's up to you. You can decide if you're going to do that or not. Okay, so really, this is almost the end here. But there are 2 sample problems, 1 and 2, and you'll see these go along with a couple of things that are in today, the suggested part of the assignment. In practice, question number 1 here. The scores of 4 roommates at the law school aptitude, the LSAT, have a mean of this, x bar equals 589, and they have this standard deviation. Here's what this tells me. They took a sample of size 4, little n equals 4. From those 4 people, they added up their scores, they divided by 4, they got this average 589, this standard deviation 37. You will have some questions where it says find the standard error of the mean. If you know the formula, this is crazy easy. You know the formula for standard error of the mean. It is standard deviation from the sample divided by the square root of the sample size. Well, we were just told that's 37. The sample size is 4. 37 over the square root of 4. The standard error is 18.5. When we get to the next part, the next video, talking about how to actually create confidence intervals for means, standard error is one part of it. The other part that makes the margin of error is the critical value, the critical T star. Now, Mr. G is going to spend quite a bit of time going through here telling you how you could do that using table B in the back of the book. You're not going to do that. Even if we were together in class, I've never had people use the back of the book. I'm always going to have you use inverse T on your calculator. And so I'm going to show you how to do it with your calculator. I'm going to get to the point here on this where all of these answers are given, and then we'll talk about them and how you would do them on your calculator. Okay, Here it is. Now you can see all of these answers are here. I do want to talk through this process a little bit and what I would do on my calculator to find these critical t-stars. What this is doing is it's saying, hey, what if you want to find a 95% confidence? Or what if you want to find a 99%, a 90% confidence interval? Here's the idea. And it also has to tell you what is your sample size, because your sample size influences what the degrees of freedom would be. So these I'm going to skip over. I'm going straight to F. Nope, E. A 95% confidence interval with a simple random sample of 15 observations. Here's what that's saying. Now I'm going to use this picture up here. This is a t-distribution. You can't really tell without labels on it if it's normal or if it's a t-distribution or what, because they look the same. A 95% confidence interval is where would we have to go so that we would have 95% of the values in the middle. If there's 95% of the values in the middle, as Mr. G points out down here, he's saying, oh, that means there's 5% in the two tails, 2.5% on the right tail and on the left tail. Now here's what you're going to do then. You're going to go to your calculator, do the inverse t command, and tell it 0.025, and you have to tell it the degrees of freedom. You have to tell it the degrees of freedom. So I'm going to show you that on my calculator, hopefully. All right, here's my calculator. Oops. Here's my calculator. Okay, inverse t is in the same place as our norm CDF and our inverse norm. Second, distributions. It's not normal PDF, it's not normal CDF, it's not inverse norm, it's inverse t, right? Again, if you have a TI-83, you're going to have to enter the code to make this happen, but it's not terrible. There's a link, again, in the Chapter 8 document. Inverse t, you tell it two things. Area, now it doesn't say it, but this is the area. It's going to find the place that you would have to go to find the area below. In the problem we were just talking about, we wanted 0.25, and the degrees of freedom was 15. So I'm going to type 15 here. Inverse t says, oh, you would have to have a z-score, except it's on a t-distribution, of 2.1314, blah, 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 whatever. If you go out, not 2 standard deviations, but a little bit more than that, 2.13 standard deviations, negative and positive. The critical value t-star is always given as a positive. We just found the place. Where would you have to go to get the bottom 2.5%? Okay. Now, I do want to show you this because sometimes that you will get the exact same thing if I told my calculator inverse or second distributions inverse t. I'm going to tell it. Now, I was looking for that middle 95%. If 95% is between my hands, that means there's 5% on the outsides, 2.5% in each tail. So I did 0.025, and it found that lower part down here. I could find this upper one, because that one was negative, but now I have to tell my calculator not just the 95% that's between my hands, but the 2.5 that's below, and I would tell my calculator 0.975, still with 15 degrees of freedom. And note, I'm a genius. If you type in the correct numbers, it helps. 0.975 with 15 degrees of freedom. And notice I got the exact same thing because the top 97.5% and the bottom 2.5%, because of its symmetry, it's the same. Either way. Do the inverse t thing a couple more times and just practice this, right? Inverse t, the two things that you have to make sure you remember. You have to tell it as a decimal. It will always, always, always tell you the area that's below what you put, or it'll tell you where you have to go to have this area below it. And you always have to tell it degrees of freedom. Degrees of freedom, 1 less than the sample size. If they tell you the sample size was 20, you have to put in 19 for the degrees of freedom. And then it's just all inverse t from there. These are what the answers should be. You can practice those a little bit. If you have questions, of course we can talk in a Zoom meeting or whatever. But that's really it for today. Standard error and finding t-star using your inverse t, and we will talk about the rest in the next video.